All right, looks like we're up and running. Sorry for the delay. Audio issues. Let me know, make sure you can hear me. Hopefully you can hear me. I think we're doing all right. Let me jump over to the slides. There we go. Sorry, now I can just check here. Sorry for the delay. Okay, I can hear myself. Good. Yeah, I've got an old webcam with a really flaky microphone, and sometimes it works and sometimes it doesn't, and I have to plug and unplug. And I tried switching to a headset microphone, but the headset microphone has an annoying buzz because Surface tablets don't have grounded plugs. Anyway, not your issue. Time to tackle eigenvalues and eigenvectors. This is hopefully it. We'll see how this goes. This is the last thing that we need to do. Is properties of eigenvalues and eigenvectors. We're going to do a couple more examples going over the how do you find eigenvalues and eigenvectors, and then try to get into a little bit of understanding why these are useful and why people care about finding eigenvalues and eigenvectors. Okay, so let me give you a warm-up problem. Hopefully you had a chance to look at this while we were getting things ready. I noticed there's a typo on the website where the slides are. The new slides are up, but I have the wrong, it says March 26th there. It says March 26th twice. That second March 26th is actually March 31. I'll fix that when I upload the annotated slides. And by the way, in case you didn't catch on to that, these slides, the kind of empty slides, those are on the website there ahead of time. And once we're done with the recording, I'm taking the annotated slides, the stuff that I've written on, and I'm putting those up as well. So you've got both of those available to you. All right. So how do we find eigenvalues and eigenvectors? We'll recap this in a bit, but remember that the first step in finding eigenvalues and eigenvectors is getting this characteristic polynomial. So the characteristic polynomial, we call it C sub A, is defined to be the determinant of x times the identity minus a, right? And so in this case, for the 3 by 3, right, x times the identity as a matrix is just x 0 0 0 x 0 0 0 x. So we take that matrix, we subtract off the entries for a, and we see what we get. Okay. So we're doing a determinant. So it's going to be x minus 3, 0, 0, minus 1, x minus 1, 1, minus 5, minus 1, x minus 3. Remember, we're subtracting the entries from a. Some people will do a minus x times the identity because it's a little easier to remember. You just subtract x's down the diagonal. Right, so some people kind of like doing that. You just go minus x, minus x, minus x down the diagonal. Right, so subtracting x's down the diagonal. That works too. The only downside with a 3 by 3, if you do a minus x times identity, is when you multiply everything out, you're going to get a minus sign in front of the x cubed term. And some people find that minus sign really throws them off when they're trying to factor. It's totally up to you which way you want to do it. Now, in this case, of course, we have a little bit easier time factoring. We don't have to worry about factoring the whole cubic because if we expand along the first row, we have 2 zeros there, right? So we just have to do the 1 1 entry times the 1 1 cofactor. Okay, so we have x minus 3 times this 2 by 2 determinant, x minus 1, 1, minus 1, and x minus 3. So now we just multiply out that 2 by 2 determinant, x minus 3. So we have x minus 1 times x minus 3 minus minus 1, so plus 1. Okay. Now leave that x minus 3 out front, because remember your goal here is to factor. If you've already got a factor, don't resist any temptation you might have to multiply it through, because we want factors. We've got one. It's making our lives easier. Inside the parentheses, or that second pair of parentheses, we do have to expand and simplify, because we have got to incorporate that plus 1. Okay, so we multiply this out, just doing FOIL. X squared minus 4x, okay, plus 3 plus 1. So we have x minus 3 times x squared minus 4x plus 4, and that works out to be x minus 3 times x minus 2 squared. All right. So we get two eigenvalues. One is repeated, right? We get lambda is equal to 3, and we get lambda is equal to 2, right? And that lambda equals 2, we sort of get that twice. The language that we tend to use for this is we say that this one here has what we call multiplicity of 2, right? That factor appears twice. Okay, so now we've got the eigenvalues. We want to find the corresponding eigenvectors. We'll do the lambda equals 3 first, okay? So for that lambda equals 3 eigenvector, or eigenvalue, we want to find the eigenvectors. So what we do is, remember that the eigenvectors come from solving a minus lambda times, so we got a minus 3 times the identity. And we basically want to solve the homogeneous system that has this as the coefficient matrix. Put another way, if you did the last assignment, what we're trying to do is find the null space of this matrix, a minus 3 times the identity. Or you can think about it as finding basic solutions to a homogeneous system, however you want to think about this. So we subtract 3 down the diagonal. We get 0, 0, 0, 1. So 1 minus 3 here gives me a minus 2, right? Minus 1. And then 5, 1, 0. Okay? Pretty typical of eigenvalues, eigenvectors, right? I mean, we want the whole point of the eigenvalue is that your matrix is going to not be invertible. So here we get a row of zeros right away. If you don't get it right away, you are going to get it eventually, right? Once you reduce. So now we think about doing some row operations. I'm not going to do all the row operations for you because it's kind of time consuming and it's not that exciting. I'm going to basically, what am I going to do? I'm going to use this 1 to get rid of that 5, but I'm also shuffling the rows as I go, okay? So I'd have to do 5 times the second row added to the third row, but then I'm shifting things up, or minus 5 times the second row added to the third. So 5 minus 5 gives me a 0. 1 plus, so I'm going to do minus 5 times minus 2 is plus 10, added to 1 gives me 11. And then I'm going to get minus 5 times minus 1, added to 0, I get 5, and then 0, 0, 0. Okay, a couple more row operations to go. 0, 1, 5 over 11, 0, 0, 0. And so if I take that and I add, I'm going to get rid of that 2 there. So I'm going to do 2 times 5 over 11. So that's 10 over 11 added to minus 1. I get minus 1 over 11. Okay. Okay. Question from Sarah. So when you're solving, the order doesn't matter. Like I was saying, like when you're writing out that characteristic polynomial, the difference if you switch the order is going to be, in a 3 by 3 case, is going to be a minus sign. What it's going to look like when you multiply out that determinant, right? If you switch the order, then instead of having x minus 3 and x minus 1, x minus 3, you're going to have 3 minus x, 1 minus x, 3 minus x. And so it'll work the same, but this will be a 3 minus x. Okay, this will be a 1 minus x times a 3 minus x. That's going to still be a plus 1. And so the only difference is instead of having like x minus 3, you get 3 minus x. And some people, when they're doing algebra with polynomials, they like to have the x out front. right? That extra minus sign throws you off sometimes. On the other hand, if you find it easier to set things up by just subtracting x down the diagonal, you can do it that way too, right? Either way is good. Okay, so we've got it down to here, and by the way, let me add a note here. When you're reducing these matrices, right? I mean, by now you're all experts on row reducing matrices. We've been doing it all semester long. You've got lots of practice. Oh, sorry. So once you found lambda and you're plugging it in. So you mean when we're finding the eigenvector? It doesn't matter. I like to do a minus 3 identity. If you want to do 3 identity minus a, it's going to be the same. The only difference if I did 3i minus a, right? The difference is going to be that I'll have 0, 0, 0, minus 1, 2, 1, minus 5, minus 1, 0. And when you get it down to reducer echelon form is going to be the same, right? Because you would at some point you're going to multiply that row by minus 1 to get rid of that minus sign, right? You're leading 1. You'll get the same answer either way. So whichever way you want to do it, it's fine. You'll get the same answer. The one thing I was going to mention as well, because you've already done lots of work here, right? Finding reducer echelon form. You can find this using the computer if you want. Okay, right? You're doing everything as take home now, right? There's no timed exams. There's no limitation on types of calculators or anything like that. Sorry, that's not really legible. Let me try that again. When you're writing up your work, right? The things that I want to see when you're doing this, I care about, do you actually understand what you're doing when you're finding eigenvalues and eigenvectors? Do you know how to set things up? Do you know what the steps are? Right? Ultimately, I mean, when you're doing math in the age of computers, you should learn how the Gaussian elimination works. You should learn that algorithm once in your life just so you understand what's going on. But when you're solving problems, right, you should think that a lot of time the goal in solving problems is going to be to kind of get things to a form where you can ask the computer to do the mechanical stuff for you. And yes, there are subroutines that will just find the eigenvalues and the eigenvectors. That maybe is kind of cheating at this point, right, because we want to understand how this works. And if you just ask the computer for the eigenvalues, you're not going to get an understanding of how things are going on. But if you ask the computer to reduce your matrix, that's fine. I think that's totally reasonable. Okay. So in the end, what does this tell me? This reducer echelon form. So if my vector was say x, y, z, and I have that a minus 3i times x is equal to 0. Well, what I get from here is that x minus 1 over 11 z is equal to 0, right? And y plus 5 over 11 z is equal to 0. That's what that reducer echelon form is telling me. Now let me grab myself another page so we have some more room to work here. Okay, and let's carry that over to the next page. So what we have, so let's try to remember that, 1 over 11, 5 over 11, okay. So for lambda is equal to 3, our eigenvector is this. So x is 1 over 11 times z. Y is minus 5 over 11 times z. And z is just z. Z's a free variable, right? So we're free to choose whatever value we want for z, right? When you're finding an eigenvalue, we talked last time about the fact that Eigenvectors are really only defined up to scalar multiple, right? So any scalar multiple will do. The only value you're not allowed to plug in for z is 0, because eigenvectors have to be non-zero. So we can plug in any value that we want for z, right? Z is our free variable in this system, because we see that we have no leading one in the z's column. Okay, so what we should get is, if we take, I would say a convenient value for z here would be to take z equal to 11, right? So we don't have fractions. And then x is going to be 1, minus 5, and 11. And if we want to know whether or not I've done things correctly, let's check our work. A times x. Okay. So I do have to jump back and remember what a is. 1, 1 minus 1, 5, 1, 3. Okay. And that was 3, 0, 0. Okay. 1 minus 5, 11. Okay. Let's multiply and see. First row, we get 3 times 1, right? We're going to get 3 times 1 is 3, 0, 0. So we just get a 3. In the middle row, I'm going to do 1 times 1. 1 minus 5 minus 11. So that's minus 16 plus 1. I get minus 15. And then in the last one, I've got 5 minus 5 plus 33. I get 33. And that is indeed 3 times 1 minus 5, 11. Okay? Works. Good. Okay. Now we move on. We also want to find the eigenvalue for lambda is equal to 2. Okay? So I do a minus 2 times the identity. Fortunately, I have a sitting right there. I have 1. So 1, 0, 0. So now I'm subtracting 2 down the diagonal. 1, minus 1, minus 1. And then 5, 1, 1. Okay? So these diagonal values here, right? 3 minus 2 is 1. 1 minus 2 is minus 1. 3 minus 1 is 1. Okay? So I want to get that down to reducer echelon form. 1, 0, 0, 0, minus 1, minus 1. I can use that 1 to clear out the zeros, right? And the other stuff's not going to happen, not going to change, right? This 1 gets rid of that 1, and the 5 and the zeros there mean that these stay the same. Okay? And actually, that gets us to there. And now we can see right away that the reducer echelon form has to be that. Okay? So now we say, okay, if we start with, say, x equal to xyz again, then we need, and we put a minus 2 identity times x is equal to 0. What does that tell me? Well, this first row here just says 1x, right? So x is equal to 0. That's all it says, right? So x has to be 0. Okay. And it says that y plus z has to equal 0. That's what the second row says. So y is equal to, say, minus z. So the eigenvector you get for the second eigenvalue would look like 0 minus z, z. Okay? And if we put z equal to 1, seems convenient. And maybe we should give these names, right? Like call that x1, call that x2, because they're different vectors. Putting z equal to 1 gives us second eigenvalue of 0, minus 1, and 1. Okay, so there's our first warm-up calculation. Now, there's one thing I want to draw your attention to. This is going to be sort of important in the sequel as we start looking at properties. Notice that we started with a 3 by 3 matrix, and we only got 2 eigenvalues because one of the eigenvalues was repeated, right? We had 3, and lambda equals 2 shows up twice because of the repeated root. Okay. Now, in the last class, we did another example where there was a repeated eigenvalue, but in that one we actually got, when we got to that repeated eigenvalue, we got 2 distinct eigenvectors that went along with it, right? When we solved the system, when we solved that homogeneous system for that repeated eigenvalue, we found that we actually got 2 basic solutions, right? So we got 2 different eigenvectors. This time we only get 1. We only get 1 eigenvector for that repeated eigenvalue. So this has relevance for a kind of a problem that we study in the context of eigenvalues and eigenvectors, which is the so-called diagonalization problem. And we're going to get into that. And essentially, diagonalization comes down to the following question. If you have, say, an n by n matrix, how many eigenvectors do you get? How many sort of independent eigenvectors do you get? Independent in the sense that there's no eigenvector that can be written as a linear combination of the others. And if you have enough, and in the 3 by 3 case, you would need 3. You'd need 3 different eigenvectors. If you have 3 different eigenvectors, then you can diagonalize. But if you only get 2, like happens here, then you can't. You actually can't diagonalize. The best you can do is get to an upper triangular matrix. We'll talk about that. Okay. So there's the warm-up example. Just pausing for a second to see if anyone has any other questions. Looks like we're okay. Onwards. So this is just a recap. I'm going to go quickly through these next few slides because these are basically pulled from the last set of slides, okay? So just to remind you what we're doing here, right? Everything comes from this eigenvalue equation, right? We are trying to find a scalar lambda and a vector x so that a times x is the same as lambda times x. This is the eigenvalue equation. Last time we went over how do we actually find these things, and we said, well, you can rearrange this equation, and you could rewrite this equation to say, well, this is the same thing as saying like a minus lambda times the identity times x is equal to 0. And if you rewrite the equation like that, then you realize, well, what you're looking for here are solutions to some homogeneous system of equations, and you want non-zero solutions, right? And you can only get non-zero solutions to a homogeneous system if the coefficient matrix is not invertible, right? And so what we want, right, we want that coefficient matrix to be non-invertible, which means we need this determinant to be 0, right? If that determinant is 0, that guarantees that our matrix isn't invertible, and that guarantees that we have non-trivial solutions, okay? And so what we're looking for is we're just looking for the roots of this polynomial, right? This, it's a determinant, but it is a polynomial. Once you expand it all out, just like we saw in the example we just did, once you expand it out, you get a polynomial. And so you're looking for the roots, right? The values that make that polynomial 0. Those are your eigenvalues. Once you find them, you can plug them in and come back and solve this equation. Okay. Let's do one more example. Find the eigenvalues and eigenvectors. This looks like sort of an intimidating one, right? Let's give it a try. This one was in my notes. I wrote this one up a while ago, and I confess that I don't remember how difficult this is. We'll see if we can do it by hand. I might be setting myself up for failure, but it's always fun to watch your profs fail at these things, right? On camera, YouTube Live, it should be good. Let's see how it goes. So first thing we got to do, find that characteristic polynomial. Okay. So we want determinant of xi minus a. So we get our x's, and now we subtract off the entries of a. Minus 4, minus 2, minus 1, minus 2, 3, 1, minus 10, minus 8, plus 3. Okay? So now we try to expand. And you could try to kind of clean things up with row operations. It gets tricky. Because you got variables in there, I think the safer bet is typically just to sort of do a cofactor expansion and try to simplify. So let's see how it goes. All right. Do x minus 4 times x minus 3. We have 1 minus 8 x plus 3. Okay. I'll go along the first row. So we'll go this way. So minus 2, right? We always change the sign in the middle. Minus 2, 1, minus 10, x plus 3, plus 1. And then we have minus 2, x minus 3, minus 10, minus 8. Okay. So let's expand and we'll see how this thing goes. All right. So x minus 3 times x plus 3. I'm gonna speed this up a little bit. That's the difference of squares. I've got x squared minus 9. And then I'm going to add 8. And then I've got 2 times minus 2x minus 6 plus 10. And then I have 16 plus 10x minus 30. Okay. Yeah. All right. This is looking a little scary. Let's see how it goes. X minus 4, x squared minus 1, 2. Let me factor out. Oh, come on. My computer is glitching on me. Okay. I don't know why that's not going away. Let me pull out a minus. So minus 4 times x. So this is going to be minus 6 plus 10, right? So this is minus 2x plus 4. So if I pull out the minus 2, I've got x minus 2 there. Okay, and then on the last one, I've got 10x minus 14. Oh. Yeah, so question from Jacob. You can, yeah, so as far as when can you do row operations and when can't you? You can't do row operations before subtracting the x. So you can't simplify the matrix and then set up the determinant. That's going to get you the wrong answer. If you want to set up this determinant, if you want to get to here and then do some row operations to try and simplify, you can. You just have to deal with the fact that when you do those row operations, there are going to be variables involved, and that's gonna cause trouble. But if you try to do row operations here before you do that, you won't get the right answer. It's going to mess you up every time. Okay, so that is, yeah, something to be mindful of. Okay, let me have a look to see, does anything kind of clean up over here? We have minus 4x plus 8 plus 10x minus 14. So that is 6x minus 6. So that's 6 times x minus 1. Oh, I'm in luck, right? This is x minus 4, x minus 1, x plus 1. And then that whole thing is just 6 times x minus 1. So there we go. I can erase again. So then I have 6 times x minus 1. And so the key here is x minus 1 shows up as a factor in both of them. So I can use group factoring to do x minus 1. And then I have, if I multiply the x minus 4 times the x plus 1, I've got x squared minus 3x minus 4 plus 6. So that's going to be plus 2. So here's what I get. X minus 1 times x minus 1 times x minus 2. All right. Oh, hang on. Question from Mitch. Negative 2 is supposed to be positive 2 in the matrix. I think we're okay. Let me know, yeah, if I did mess something up. Give me a shout. Remember that we're doing minus a, right? We're taking x times the identity, we're subtracting a. So we should switch the signs for every entry. So it should be minus 4, minus 2, plus 1, minus 2, minus 3, plus 1, minus 10, minus 8, plus 3. Let me just make sure I didn't do anything else wrong with that. I think we're okay. And that plus sign there, remember that this this plus sign here comes from the fact that we have to do minus 2 and then minus 1 to the 1 plus 2. There's that sign factor in the cofactor. So I think I'm okay. And here I've got, just so you know where that factoring came from, this is x squared minus 3x plus 2, and that factors as x minus 2 times x minus 1. All right. So this is another one where we have a repeated eigenvalue, right? We have lambda is equal to 1, and we have lambda is equal to 2. Okay. Yeah, let's give it a try. Let's see what we can do. I'm gonna do, yeah, let's do them both. I'm kind of tempted to sort of move on, but no, let's do it. Okay. Add one page. Okay. Did I get my page? Where did my page go? Try that again. Insert a new page. Good. Okay. So, let's do the lambda is equal to 1. So this is the one that has the so-called multiplicity of 2. So, my matrix, I have A minus 1 times the identity, right? So let me just remind myself of my matrix. 4, 2 minus 1, 2, 3 minus 1. And 10, 8 minus 3. And I'm going to subtract off, it's just the identity, right? 1, 0, 0, 1, 0, 0, 0, 1. Okay, so I get this. I get A minus I is 3, 2 minus 1, 2, 2 minus 1, and 10, 8 minus 4. Okay, well that's a real mess, isn't it? Let's try to simplify. I don't know why I give myself such a hard example to do. In class, maybe this makes sense. I'm going to do row 1 minus row 2 into row 1. I'm going to do row 3 minus 5 row 2 into row 3. Let's see what I get. 1, 0, 0. Oh, that's convenient. 2, 2 minus 1. And then I get 0. 8 minus 10 is minus 2. Minus 4 plus 5 is minus 1. Okay. Good. We're doing all right. Let me know if I've messed anything up. Yeah. I feel like those should cancel exactly. Well, we'll live with it. Yeah. I have a mistake. But let me think about that for a second. Yeah, it should be 8 minus 10 is minus 2, minus 4 plus 5 is 1. There, that's better. Okay, just didn't add properly. Okay, so then I can kind of get it all the way down to reducer echelon form, and I'm going to get 1, 0, 0, 0. Well, okay, not quite reducer echelon form. We're going to do this. I didn't get the leading one here, yeah? Now you can do that step if you want, divide that row by 2. Sometimes it's nicer to have kind of the integer powers. So now I come and I say, okay, if a minus I times x is equal to 0, and x is, say, x, y, z, then I'm going to get that x has to be 0, and 2y minus z has to be 0. So we could say z is 2y, yeah? So I would get 0, y, 2 times y, and if I put y equal to 1, 0, 1, 2 as an eigenvector. So again, I only get one eigenvector for that repeated root. Okay, and now what was our other eigenvalue? The other eigenvalue was 2. Okay. For lambda equals 2, I'm going to leave that as an exercise because I want to move on and I want to do some more stuff for you. Okay, we've already been at this for a little over half an hour. So, see how everyone's doing. We're doing all right. Again, if we want to check our work, make sure that that actually works. It should be the case that if I do a times x, I should get x, right? Because 1x should be x. Let me see. We'll just check our work and then we're going to move on. Okay, so 4, 2, here's my matrix. 4, 2, minus 1, 2, 3, minus 1, 10, 8, minus 3. Multiply by 0, 1, 2. And we're going to get, let's see, 0 plus 2 minus 2 is 0. And then I get 0, 3 minus 2 is 1, 8 minus 6 is 2. Okay. Checks out. Okay. All right. Now let's move on. We'll talk a little bit of theory. We can't squeeze this all in today, but we'll do as much as we can. You can take a look at the rest later on. The main thing I'm going to expect from you all on an exam is pretty much being able to do the calculations. Okay, question from Sarah before we moved on. Yeah, I'm cheating a little bit. I should use z as my free variable. The reason why I didn't is, you know, if we're following the rules that we did back in, what was it, chapter 4, I should have taken row 2 and multiplied by 1/2, right, to get y is equal to 1/2 z, where z is free. So I could have done that. I could have done this. I could have done 0, 1/2 z, and z, where z is free, and then just put z is equal to 2, and I get to the same place in the end, right? Once you do enough of these, because you're always solving homogeneous systems, and typically once you get it down to reducer echelon form, solutions are looking relatively simple. Sometimes you kind of cheat a little bit and you take shortcuts to avoid fractions because, you know, we don't always like fractions. The other thing that you might do, like I'm trying to choose my free variable so that I don't get fractions, right? I want to have integer entries, and that's fine. But actually, in a lot of applications, you want unit vectors. There's a WebWork problem that asks you for unit vectors, so watch out for that. And just as a reminder, going all the way back to chapter 3, if you want a unit vector, you got to multiply by 1 over the magnitude, right? So that's going to come up for you if you haven't encountered that already. Okay, let's talk triangular matrices. Okay. So the nice thing about triangular matrices things like trace, determinant, and even eigenvalues are really straightforward, right? Well, trace is always simple, right? Trace, you just add down the diagonal. It doesn't matter if you have triangular or not triangular, you just add down the diagonal, and that's easy enough. So trace is simple enough. Determinants, we know that determinants are pretty tricky in general, but we know that if you have a triangular matrix, you just multiply down the diagonal, right? So this first one here would have a determinant, let's call them all A. I probably shouldn't call them all A. That would be minus 60. Here the determinant would be 12. Here the determinant is 8. And here the determinant would be 12 again. Oops, determinant of A. So determinants are easy enough. The other thing is, if you think about finding eigenvalues, or you think about finding the characteristic polynomial, maybe we should call these like A1, A2, 3, 4. Okay? If I wanted to find the eigenvalues for, say, that first one, right? If I wanted to find the characteristic polynomial for A1, right? I'm going to do what? I'm going to do this determinant. It's x minus 3, minus 2, minus 1, 0, x minus 4, minus 2, 0, 0, x minus 5 becomes x plus 5, right? But when you subtract the x times the identity, it's still upper triangular. So when you do this determinant, you still multiply down the diagonal, right? You just get x minus 3 times x minus 4 times x plus 5. And so right away, we know that the eigenvalues are going to be 3, 4, and minus 5. Simple enough, okay? And then you can go about finding eigenvectors if you wanted to, right? We can do it. So if I wanted to find, so if I was doing like A1 minus 3I, so this is interesting, right? This is one of those cases where you actually do get a column of zeros, 0, 0, 0, right? 2, 1, 1, minus 2, 0, minus 8. So if you go get the reducer echelon form for this thing, you're going to find that, well, obviously that's going to stay as 0, 0, 0, 1, minus, actually you're just going to get this. That minus 8, we can divide by minus 8, get a 1 there, and then we can clear above it, so we get sort of just that. Okay, so actually what we get is that y has to be 0, z has to be 0, x can be anything, and so we actually just get an eigenvector. It's just I, 1, 0, 0. Okay, and you might similarly find that the eigenvectors for 4 and minus 5, they're going to be j and k, right? I'm not going to go through all the details. But you can play around with these, right? The point is that in all of them, if you have a triangular matrix, the eigenvalues are just the numbers on the diagonal, right? So for the second matrix, eigenvalues are going to be 2, 2, and 3, right? For the third one, eigenvalues are 2, 2, 2. It's actually the same eigenvalue 3 times. And then 2, 2, 3 again. So one of the things that you want to play around with when you're doing these is you might find that this one here, you actually only get one eigenvector. Okay, because of those ones sitting above the diagonal. These things here, they mean that when you subtract 2 times the identity, you actually already get down to this same sort of reducer echelon form, right? You just get this as the only eigenvector for that matrix. But if you remove either of those ones, then you start getting more than one eigenvector. And so you can start playing around. Like this last one here, it's actually diagonal, right? So if you have a diagonal matrix, you get actually I, j, and k all as eigenvectors, right? I and j, those ones are going to have eigenvalue 2. K will have eigenvalue 3. Play around with these, okay? Um, so if you're like the first one where all the eigenvalues are different, right? Here they're all different. Having that extra clutter above the diagonal doesn't actually matter. You're going to be able to find, if you have distinct eigenvalues, it turns out you're guaranteed to find one eigenvector for each one. And so you get 3 eigenvectors for a 3 by 3. But if you have repeated eigenvalues, then whether or not you have something kind of sitting above the diagonal for those repeated eigenvalues turns out to be important. We don't get too much into why in 1410. This has to do with something called Jordan canonical form. This is something you would see in Math 3410. So you can actually, it turns out you can move beyond eigenvectors to something called generalized eigenvectors, which are kind of fun, but it's also not something that belongs in an introductory course. Okay, so the next thing we want to talk about is this idea of two matrices being similar, right? So similar means, so we have A, we have B, and we want to say that they're similar. What it means is that you have this third matrix P that sort of interpolates between the two, right? So some people might write this as saying that P times B is equal to A times P. That's one way to write it. You could also write this as P times B times P inverse is equal to A, right? And then you might be able to write that as, say, Q inverse BQ is equal to A, where Q is just the inverse of P, right? Because the inverse of the inverse gets you back to where you started. And so what you might write, the notation you might use for this is you might say this A is similar to B. And what we're basically showing here is that saying A is similar to B is equivalent to saying B is similar to A. So you can talk about two matrices being similar to each other. For anyone that's done Math 2000, which is probably not that many of you, in Math 2000 you talk about what's called an equivalence relation. So it turns out matrix similarity is an equivalence relation. And you can actually take like all the matrices and break them up into these kind of equivalence classes. So all the matrices that are similar to one thing go in one box, and all the matrices that are similar to something else go in another box. These are interesting things to play with. We just don't have a lot of time to do it here. If you're doing that optional assignment 4, you get to explore this a little bit, but we're not going to do it here in the video. But one of the things that you can show is that similar matrices have the same trace, determinant, and eigenvalue, right? Determinant is pretty easy to show, right? Because if I take so determinant of B being the determinant of P inverse A times P, remember that determinants have this multiplicative property. That's the determinant of P inverse times the determinant of A times the determinant of P. And then we also had a relationship that says the determinant of P inverse is 1 over determinant P, right? And so those cancel out. And so determinant of B is equal to determinant of A. And you can similarly show that the eigenvalues are the same, and essentially what you're doing there is you say, well, okay, suppose I have A minus lambda times the identity, and I multiply on either side by P inverse and P. Then I'm going to have P inverse A P minus P inverse times lambda I times P. Okay. So P inverse times A times P is B. And, well, over here, that lambda is a scalar. You can bring it out front. And then you just have P inverse times P, which is just the identity. So you get B minus lambda times the identity, right? And so that means that what this tells me is that B minus lambda times the identity is similar to A minus lambda times the identity. And that means they have the same determinant, right? So the two matrices have the same determinant, means that A and B have the same characteristic polynomial, so they have the same eigenvalues, right? So Now you start looking at this and you feel like, okay, yeah, I have this like awesome strategy now for finding eigenvalues and eigenvectors, right? Because finding eigenvalues is hard in general, but finding eigenvalues for triangular matrices is easy. So then you say, hey, maybe what I want to do is find a triangular matrix that's similar to my matrix, and then I can just find the eigenvalues from there. Well, unfortunately, it's not so easy. There's good news and there's bad news, right? The good news is that every n by n matrix is similar to a triangular matrix. So you can always find, so that means that we can always find P, which is invertible, and we can find B, which is triangular. Let's say upper triangular if you want, so that B is equal to P inverse times A times P. You're guaranteed that you can find those two matrices. And so you might think that this gives you a strategy for finding eigenvalues and eigenvectors. The catch is that the way you find B and P is by finding the eigenvalues and eigenvectors. So there are no shortcuts, right? Like I mentioned this last time, there are no shortcuts for finding eigenvalues and eigenvectors. Not really. There are some computational tricks, but there aren't great shortcuts, unfortunately. The only one thing I want to warn you about is if you're working over the real numbers, this isn't quite always true because you might not be able to find eigenvalues because you might not be able to factor the characteristic polynomial. If you're working over the complex numbers, you have this fundamental theorem of algebra, which guarantees that every polynomial can be factored. Okay, so you can certainly do this sort of triangularization over the complex numbers. It's guaranteed. Okay. Now, triangular is great. Diagonal is even better. Right. So what we'd really like to find is we'd like to find a diagonal matrix that's similar to the matrix we started with. Okay. This is kind of a thing that we want to do. One reason why you might want to do this, and this is on another slide, but I think I might not get to it. So let me just tell you about this here. So one of the things that you might want to do is say, okay, maybe you want to find a to some power, like a to the 10 or something, right? And it turns out you can diagonalize. So you can find that a is equal to P D P inverse, right? So then a to the 10 is going to look like P D P inverse, P D P inverse, right? P D P inverse, and you're going to do that 10 times. But then you notice that all these internal P inverse P, they cancel, right? This P inverse is going to cancel with the next P. That P is going to cancel with the P inverse that was right before it. And you get down to something that just looks like just P times D to the 10th power times P inverse. Okay? Now that's great because powers of diagonal matrices are super easy, right? If I wanted D to the 10, D to the 10 just looks like lambda 1 to the 10th, lambda 2 to the 10th, and so on, right? Powers of diagonal matrices are super easy. Powers of general matrices are really hard, right? You'd have to multiply A by itself 10 times. Even for a computer, if A is large enough, that's going to be tricky. So this is one reason why you might want to diagonalize. There are actually a lot of applications that involve finding powers of matrices. So things like Markov chains and discrete dynamical systems. There's a lot of things where basically every time you multiply by a matrix, this is sort of like iterating and going to the next step. So a lot of like applied probability problems, things like this, you end up using matrices for that. And powers of matrices. So there are lots of situations where you want to be able to efficiently compute powers of matrices. And so if you can diagonalize, you're happy. Now, there's this theorem at the bottom. We didn't spend a lot of time talking carefully about what it means to have a basis. So a basis basically means that you have enough eigenvectors that every other vector can be written as a linear combination of those eigenvectors. So think about like IJK. IJK form a basis for R3. right? In general, in n dimensions, you need n vectors, and they need to be independent in the sense that you can't take one of them and write it in terms of the others. So you need to be able to find enough eigenvectors, right? So those examples we saw where we had a repeated eigenvalue and we only got one eigenvector, those are matrices that cannot be diagonalized, okay? If you have a repeated root in your characteristic polynomial, you need to be able to find enough eigenvalues to go, or eigenvectors to go with it. So this is kind of what it boils down to for the most part, okay? So here's a quick example. Well, I hope it's quick. Yeah, let's do this one. We'll do it fast. I've got about 10 minutes left. So I've got that. Yeah, let's do this one. Okay, so the way we decide this is we say, okay, let's look at the characteristic polynomial. Okay, so we're going to do x minus 2, 0, minus 2, 0, x minus 2, 1, minus 1, 1, x minus 4. Okay, so choose a row or a column and expand. This time maybe I'll go down the first column. Okay, so I get x minus 2, x minus 2, 1, 1, x minus 4, minus 1 times 0, minus 2, x minus 2, and 1. Okay, well, the good news is this one's going to be a little bit easier to factor. Okay, I'm going to get x minus 2 times, okay, x squared minus 6x plus 8 minus 1. Okay, so this part here comes from doing that product, and then we subtract 1, right? And now on the other one I've got minus 1 times minus 2, but we subtract, so minus, there's a plus. A lot of minus signs there to keep track of. I think I got it right. So what we like is common factor. Group factor whenever you can. So we have x squared minus 6x plus 7 minus 2. X minus 2, x squared minus 6x plus 5. Okay, x minus 2, x minus 1, x minus 5. Now, of course, from here, what I should do, I'm not going to do the whole thing, okay, because we're time limited. I don't want to make the video go on, and I got to go in 15 minutes. I got to go teach my calculus class, and somewhere in between there, I got to get a kid down for a nap. But we can actually already say that the answer is yes, okay? Because we have 3 eigenvalues, 1, 2, and 5. Each one gets an eigenvector. And there's a theorem, it's a bit tricky to, we're not going to try to prove it, it's a slightly tricky proof to give in a 1410 level course, but you can prove that eigenvectors coming from different eigenvalues are always independent. So if we find one eigenvector for each eigenvalue, we get that basis of eigenvectors that we want. Okay. So anytime that you have no repeated eigenvalues, diagonalization is guaranteed. Okay. And so the part that I don't have time to tell you, I don't have time to do it, but let me tell you this, okay? The matrix P, if we do this, if we do x1 as the first column, x2 as the second column, and x3 as the third column, where x1 is the eigenvector corresponding to 1, x2 is the eigenvector corresponding to 2, x3 is the eigenvector corresponding to 5. If we just set up that matrix, we find those 3 eigenvectors, we put them as columns of a matrix. it turns out that if you do P inverse times A times P, what you're going to get is 1, 0, 0, 0, 2, 0, 0, 0, 5. Okay? And if you put those columns in a different order, all that's going to happen is you swap the order. So if I swapped x1 and x2, what would happen is those two eigenvalues would change place, right? So the eigenvalues are going to show up in that diagonal matrix in the order corresponding to the order you put the eigenvectors in. Okay, so we'd find the eigenvectors corresponding to the eigenvalues, we'd slap them into that matrix, and then we could calculate that this gives us this diagonal matrix, right? Here's our diagonal matrix, D. It's a good exercise to try. Okay. All right. So this is just repeating what I just said. If you have distinct eigenvalues, so no repeated roots in that characteristic polynomial, the corresponding eigenvectors are independent. And so if you have all distinct eigenvalues, then you're guaranteed that you can diagonalize. That's all that's saying. Okay. If you have repeated eigenvalues, this is where things get interesting, right? So if you have eigenvalues with higher multiplicity, meaning that you have these powers showing up, right? So we have something like that x minus 2 squared, right? 2 shows up twice. It's a repeated eigenvalue. Well, then what you do is you go and you calculate this so-called eigenspace. So the eigenspace is just it's a null space if you did that on the assignment, right? You're just finding all the basic solutions to a homogeneous system. And so what you need is you need the number of basic solutions to equal this value, to equal that k. Okay, so if an eigenvalue is repeated 3 times, you need 3 basic solutions when you solve the homogeneous system for the eigenvectors, right? If you get fewer, right, if an eigenvalue is repeated 3 times, but you only get 2 basic eigenvectors, then you can't diagonalize. This is pretty much what it boils down to. So there's 2 things that stop you, I guess. The other thing that could happen is you can't factor the characteristic polynomial over the reals. You need complex numbers. That's one of the reasons we talked about complex numbers, is if you want to be able to guarantee that you can always factor this polynomial, well, then you need to use complex numbers, because not every polynomial factors over the reals. Over the complex numbers, we're guaranteed that we can factor, so we might have some complex eigenvalues, we might have corresponding complex eigenvectors. That's okay. We can work with it if we have to. The thing that really stops us from being able to diagonalize is when we have like those 2 examples that we did today, where there's a repeated eigenvalue, and we go to find the eigenvectors corresponding to it, and we only get 1 eigenvector. We would need 2 eigenvectors to come along with that eigenvalue before we could diagonalize. The last example that I did last week, that's one where actually you can diagonalize, because we had a repeated eigenvalue and we got 2 eigenvectors that came with it. Okay. There are some examples in the textbook. I encourage you to kind of look these things over. Okay. I don't have time to do another example because I want to close this out in just a couple of minutes. You can try this if you want to try this as an exercise. You can try it, and you can always post on the forum. Okay. I'm happy to work through these examples for you on the forum if you want to see them later. Or you can book me for a Zoom office hour, right? We have those bookings available as well if you wanna grab me for one of those. We can go through those examples. Okay. So yeah, by all means, ask me to do that on the forum. We'll have a little bit more time there. I can type it all up for you. Okay. Same thing with that one. Okay. We talked about powers already, right? If you want to find the power of a matrix, you can actually diagonalize to do it. Yeah, we already did the work on that one. I'll go over that. Make me do it on the forum, then everyone can see it, right? We'll work these examples on the forum. Okay. Oops. You can also let's skip polynomials. I don't want to talk about polynomials. The last thing I want to mention. Turns out the really interesting case is symmetric matrices. One of the reasons why we bother to tell you what a symmetric matrix is, right? So that, remember, a symmetric matrix is one that's equal to its own transpose. You can prove 2 things about symmetric matrices. One is that eigenvectors coming from different eigenvalues are orthogonal. Okay, so their dot product is 0. The other thing that you can prove is that all the eigenvalues are real. So this is one case where you don't have to worry about complex eigenvalues. You're guaranteed the eigenvalues are real. Okay, and you're also guaranteed that you can find enough, right? So symmetric matrices are one case where you are guaranteed to be able to diagonalize. And not only can you diagonalize, you can find sort of a whole bunch of eigenvectors. You can find x1, x2, right, down to xn, where a times xi is going to be some eigenvalue, right? So they're all eigenvectors. And the other cool thing is you can set things up so that when you dot two of them, okay, you get 1 if I is equal to j. So in other words, that means that the length of each vector is just 1, and 0 if I is not equal to j. Okay, and so that means they're all mutually orthogonal. And it turns out if you stick those into a matrix, if you use those to get this matrix P, it turns out that the inverse, to compute the inverse of P, you actually only need a transpose. This has a name. We say that P is orthogonal. So this process of orthogonal diagonalization for symmetric matrices is really useful in a lot of applications. We don't have time to do them all. I wish we had more time. I'm tempted to do another class on eigenvalues and eigenvectors, but I think people might want to see a little bit of review as well. I'm going to be putting up a poll for you soon asking you what you want to see. We can always, we can spend more time on eigenvalues on Thursday, but we'll try to find time for some other things as well, right? You might want some reminders on lines and planes or something like that. The nice thing about a lot of these eigenvalue problems is that they actually use a lot of what we did, right? The context for eigenvalues and eigenvectors is matrix transformations. The way we find them, we have to solve systems and we have to find determinants, right? We're computing these vectors, right? So we're doing some chapter 3 stuff. Pretty much everything, chapters 3 through 7, they all show up here, right? All the stuff that we've done shows up in the context of eigenvalues and eigenvectors. This is not what I would do to you, but I know there are people who have taken the point of view, well, because actually eigenvalues and eigenvectors involve everything we've done so far, we could do a final exam that consists of nothing but eigenvalues and eigenvectors, and I could set that up so I actually test everything in the course. I'm not going to do it, but we could, right? We could if we really wanted to. We're not going to, but we could. I'll go for a comprehensive final, don't worry. But it is sort of a nice capstone topic for the course because it does really deal with everything that we've done. Okay, looking at my time, I have to wrap things up. So we're gonna pause the stream right here. If you have any more questions on this, please get at me on the forum. I'll be happy to answer, and I'll be happy to work through some of the examples that I didn't have time to do in the live stream. We'll do them on the forum. I'll type them up. Probably won't be till tonight, once my kids are in bed, but I'll get them done. All right. Thanks for tuning in, and we'll see you on Thursday for one last class.